In this lecture, we talk about fibers of morphisms of schemes. So say we are given a morphism like this f. So from x to y, and these two are schemes, and y is a point here in y. So we can call this x the subscript y. You take the scheme x, tensor it over y with k of y. This is residue field for this corresponding to this point y in the scheme y. So corresponding to point y, recall that you have a local ring, and then you modulo out the maximal ideal with the local ring, and what you get is a residue field. So this residue field we are denoting by this kappa of y. So this thing is called the fiber of f over y, because you have this morphism f and then you have this fiber over y. So we are going to compute a lot of examples to properly understand this very important structure. So let us do example number 1. So you consider a map from a variety. So variety is defined in 3 space. So there are 3 variables. Ut is equal to s, and from 3 space you go to the affine line. So we have the simple projection map u, t and s. This gets mapped to s. So this variable just gets projected here. These two just go away. So this is a simple projection map. So the fiber now we are going to write as x a here is spec of a sub a. So a is the point over which we are going to take the fiber. So we always write spec for the scheme. So we are going to compute this a, which is going to come from a tensor product, and then we just write spec in front of it to get this. So we'll compute AA. So for AA, first you talk about this variety living here. So this is given by ut equals to s. So its corresponding coordinate ring is this. And for this, for A1k, you already know that ks is the space. And then you have the maximal ideal corresponding to point A, which by null starts as s minus a. So that s minus a is essentially you're setting s as equal to a. So if you just consider it as this, you will just get this k as the residue field, because s is setting as a. So all polynomials you are evaluating at point A. You take the tensor of these two, you will just set s as a, and that is what you get. So k ut minus a. This is a of this sub a. And then you put spec in front of it, so you get xa. So xa, if you want to compute, this is just spec of this thing. So now you can see for every a you have this fiber. So you keep on varying a, you keep on getting different schemes xa. So you keep on taking prime ideals of those. So this was first example. The second example looks similar, but it is slightly has slightly more things to it. So now you consider union of two lines. So xu equals to 0. So this looks something like this. So there are two lines, and this is the union of two lines given by xu equals to 0. This lives in 2 space, and then you are getting projecting it to the affine line. So this is not a simple projection. So you are taking one coordinate here, say u, and the second coordinate here is x, and then you are say mapping it to u minus x. So as you can see here, so we are writing it as minus x plus u gets mapped to t. So corresponding to this, you have this coordinate ring kxu xu. Then you tensor it over the affine line. Again, affine line is given exactly like this. So instead of s, we are putting in t. This. So now you have u becomes t plus x. So we are replacing u with t plus x, but t becomes a because you're evaluating this at a. So if you just look at this, this is just as k because this is an evaluation map at a. So this becomes t plus x. T we are saying is becoming a, so u becomes t plus x, so you can write t plus x, and this becomes a, so you get this. So this ring is nothing but k times k. So the fiber here is spec of k times k. So here a is non-zero. If a is 0, then this becomes kx modulo x square. So this is a non-reduced scheme. So we have obtained a non-reduced scheme corresponding to point 0. So corresponding to this point, you have a non-reduced scheme. So we have a non-reduced scheme corresponding to this over 0. So this is another way. So let us consider another example. So this example goes on from here, but now we have two planes glued at the origin. So this example and the next one are taken from the book Geometry of Schemes by Eisenberg and Harris. So you can again see these examples in that book, but this is an exercise, so we have solved this exercise. So now we consider a map from 4 space, which is a union of two planes. These two planes meet only at the origin, and you map it to the affine plane. So the affine plane, say, has coordinates s and t, and this A4 space has coordinates x, y, u, and v. So this is how we are mapping. Minus x plus u gets mapped to s. That is the first coordinate of this affine plane. So you take these two, you map it to the first coordinate, and then you take these two, you map it to the second coordinate. So minus y plus v gets mapped to the second coordinate. Essentially, we are using the same process here. So same process here. So now we will have two planes, and you will take the first coordinates, take their difference, gets mapped to s. Take the second coordinate, take their difference, gets mapped to t. So let us see this pictorially. So these are two planes, plane 1 and plane 2. We are taking them in 4 space. So you take some point here, x comma y, take another point here, say u comma v, and then you map it to some point here, s comma t. So you can see you have corresponding to every s, you have these 2 points mapping to it, and t comes from mapping 2 points, and these 2 points meet at the origin right here. So again, you can find this figure in Geometry of Schemes by Eisenberg and Harris. So this you can find on page 32 of Geometry of Schemes by Eisenberg and Harris. So let us come back to the algebra. So now we want to talk about the fiber. So fiber is going to be spec of this A sub AB. So we are going to find this ring, and you just take spec of it. So you have point A and B. So A and B just lies on the lower plane, and say either one of them is non-zero. If they are 0, then the behavior would be different, as we will see in a minute. So first you have this 4 space. So corresponding to 4 space, we have this 4 variables x, y, u, v, and then you have two planes meeting at the origin. So the origin, the ideal corresponding to the origin by Null-Stellensatz is this x minus 0 comma y minus 0, and this ideal would be u minus 0 comma v minus 0, and we have to take the intersection because these two planes are meeting at the origin. Now you tensor it with this a2 right here, and then the corresponding maximal ideal is this s minus a comma t minus b. So again, this is just an evaluation map. If you just plug in a for s and b for t, what you're just going to get is k, because all the polynomials you are essentially evaluating at the point a comma b. A for s, and for t you plug in b. So again, once you take the tensor product of it, we have to replace u. So you will replace this u with s plus x. So you're going to replace this u with s plus x, and this v with this t plus y. So once you make these changes, but this s and t you have to evaluate at this a and b. So now this u, which had become s plus x here, now instead of s you're putting in a, so this becomes x plus a. Here for y remains y. For t you're evaluating it at b, so this becomes b. So here v would have become t plus y, it becomes y plus b. So you have this intersection, this becomes k times k. Now if A and B are 0, so first you put in 0 here, then you take the tensor product, you first take the intersection, and then you plug the various values in. So if you plug in the various values first and then you take the intersection at 0 0, this becomes x square xy y square. So at 0 0, so if you plug it in here, then you will just get x comma y because both of them are the same ideals. But you plug in 0 0 right here. So if you plug in 0 0 here, then you will have again s plus x here and t plus y here, but you have to take the intersection first and then you plug in the values for u and v. So we plugged in the values for u and v. For u you plugged in s plus x, and v you plugged in t plus y, and instead of s you put in a and y you put in b. So again you have to first take intersection and then plug in the values. That will give you x square comma xy comma y square. Now this is a three-dimensional space. See, this is a two-dimensional space, this is a three-dimensional space. So obviously this is coefficients of x, coefficient of y, and constants. So all three of them come here. So you get constants and constants again corresponding to y. So our fourth example, this is from Hartshorne. So you can see a nice picture corresponding to this in Hartshorne. So in A3K, in three-dimensional space, you have a variety defined by ty equals to x square. And then you project it to the affine line. And the projection is given as x, y, t, and then you project to the third coordinate. So now we want to talk about the fiber. So fiber is spec of this ring. With this ring is given as, so corresponding to this, we have this ring here. You are in 3 space, and then you modulo out by our variety. And here you just have affine space, so you just have this. So again now you have to just replace t with a, so this becomes ay minus x square for a not equal to 0. For a equal to 0, this becomes a non-reduced scheme of this form. So there is a beautiful picture corresponding to this, and you must open Hartshorne to see it. So our final example is of arithmetic schemes, and this is taken from King Liu's book on algebraic geometry, algebraic curves. So here we talk about this map, this z t1 t2 over t1 times t2 square minus m going into spec of c. So again the variety here is this, and corresponding to this you can easily replace, because we will have this t1 t2 square equals to m. So you can replace t1 by m divided by t2 square. So you do not need t1, this can be replaced. So this essentially just becomes z t1 t2 comma 1 over t2, because we can replace t1 from this equation here. So what are the fibers? So we all know what are the prime ideals of integers. You have to consider 0 and the other prime ideals. So corresponding to 0, if you localize it, you get rationals. So this we are anyway replacing by this thing right here. So you tensor it over rationals just like here. So you localize it, your local ring is just rationals over 0, because if you localize with respect to 0, you have to take the complement of 0 if you're taking 0 as a prime ideal, and then you get the you take the entire, if you localize it, then you will just get rationals. So we get this ring. At other prime ideals you can localize it with respect to prime ideals, but then you have to also modulo out with respect to prime ideals, because here we were just modulo outing with respect to 0, you just got rationals. Here you have to modulo out with respect to our prime ideal or prime number p. If you do that, you just get this f of p. Again this thing is nothing but this, and then you tensor it with f of p, you get fp t2 comma 1 over t2, and this p does not divide m. Now if p divides m, you can factor this thing again. So if you factor this thing, you will again get a non-reduced scheme. So again you can open King Liu's book, and you can see a picture corresponding to this example.